Okay, I want to look a little bit at the IDE. Um, and so when we have our different projects, it comes up and it asks you if you want the default workspace. You can have different workspaces, and that can be thought of as a collection of different projects. So by default, it'll say workspace underscore whatever version of the development environment that's currently in it. And so when there's another update, for instance, there will be a workspace 1.8, and you can pick that one and you can go back and switch between other workspaces. So you could have a collection of things that you're doing. Let's say you're doing something for digital signal processing. Well, you might want that stuff separate from the stuff you're doing for my class. So you can put it in different workspaces. The workspace keeps track of the windows, the arrangements of where things are, and the different files that you want to link into your project, all of that kind of stuff. It doesn't necessarily have the files that you are interested in that directory. If I go search under C, and we can go look for where it is, it's under your C drive, your whatever you're logged in as, STM32 cube. You're going to find a repository, and under that, you'll find cube IDE. You'll find a repository under the cube. I believe you'll find the different workspaces. But again, you can put them anywhere. That's the default. But we'll go look. You can have something in here that's somewhere else on your drive, and that can be sometimes a little confusing. And they have some samples that are buried deep, and I'll show you where all of those kind of things are. And if I open those, they're wherever you found them, but they'll show up in your workspace. So sometimes when you go, where's my file? It can be a little tricky to find out. The other thing is, I know you've been talking with Wayne on Git, and um, with GitHub in particular. And Git is a version control system, and we'll talk about it more probably around week 5 with what we look at with it. But Microsoft bought GitHub, which is one of the repositories. Git is separate from GitHub. GitHub is a repository and one of the biggest for people sharing different projects, collaborating, working on different projects. Git is the technology behind that. There's other places that will give you free accounts. In fact, I used to say, okay, GitHub used to say, okay, for public projects, something that you're willing to share, free. And if you wanted a private project, they would give you, I think they might at one time given you 5, and then it was so much a month. That's how they were making their money. And then they had some decent deals for students and gave you all sorts of things. There still is on GitHub some sort of benefits for being a student on there as well. But there's other places. Atlassian is a billion-dollar company that has something called Bitbucket. You can go and have a Bitbucket account, and you can point your cloud-based storage to them. And the big advantage before was that they would give you private repositories kind of unlimited and free. And they also had different features for commercial and things like that. And there's one called GitLab, and GitLab is really cool in that they have a bunch of their server and technologies and stuff that you can download and put your own server in your own administration, your own workplace, and just have it local. However, one of the benefits of Git in the cloud is the fact that if somebody stole my laptop today, it's out in the cloud, and any other machines that you're working on have access to it and things as well. So it's a good backup, right? You don't want to say it's on my USB stick, so it's backed up, so I'm all good, because you'll lose the USB stick and then you have nothing. And as I tell the project guys always, a few years ago, before the cloud was easier, and you didn't get things like Dropbox and Google Cloud and Microsoft OneDrive and all of that kind of stuff. I had a project group that this is before kind of MP3 players were everywhere, and they had an MP3 player, and theirs was based on a CD-ROM. They're those disk things that you used to. Anyway, they had every week demonstrable outcomes on things, and things went catastrophically bad about the second to last week, and they lost the drive, they lost everything, and there weren't kind of backups. So um, they were able to, they didn't fail, they had demonstrated previous work, but they didn't get as well as they could. You don't want to leave backups. I've had, when I used to manage the London Drugs computer department downtown years ago, and I had somebody come in and was willing to pay anything because his hard drive, he had all his client stuff on it, and he was an accountant, and that was, everything's on there. And so you don't want to ever be in that position, right? And if you know, it's easy to click, there's privacy things, but there's easy to click, just put everything in Google Cloud or OneDrive or, any of those kind of backup places. I think Wayne will probably talk to you about backups and 3-2-1 and all of that kind of stuff, right? Probably. Okay. Anyway, so CubeIDE, we have a work space, and you can have multiple workspaces, and it's where it keeps track of all the things that you're doing with that project. The actual files are probably in that workspace, but not necessarily so, depending on whether you've imported something, maybe some samples and things. And I will show you some of that kind of stuff down the road. Because I have multiple different projects in my workspace, you always have to make sure that you are working on the right thing. Oftentimes, if I have multiple things open, for instance, I might just want to click closed, or if you right click, it will say close everything to the right or close all. Sometimes I'll want to just close everything and then go have a look at, for instance, one of the projects. So I'll go and look through any, but if I highlight one, so I'm going to highlight that one here, and so I should be working on Hello World. And then you have a bunch of directories here, and I have binaries, includes, core drivers, all of that kind of stuff. And if I look at binaries, if I can, it says hello world.elf. That's the executable that I can go and load and debug and do all of that kind of stuff. When I compiled my code, if I had no errors, that kind of stuff should be there. There's also an option in the properties to make a bin file, a .bin file. And so what a bin file, it's more of just the raw ones and zeros. I can drag and drop that. You know how your discovery comes up and thinks it's a drive? You can drop the bin file onto it. So if I didn't want to open the IDE or didn't have the IDE going and I had my binary file, then I could just drag it over. I could send my binary file over to a friend that says they're not sure if their wiring's right. Maybe you've wired up the TFT display and it's not working. You could send your binary file to somebody else. They could drag and drop it onto their discovery board. It programs it. You don't even need the IDE around, and hopefully their TFT is working and you've proved that their wiring is good and that kind of stuff. Okay, so there's, by default, it just does ELF. We can, in the properties of the project, say, give me a binary file as well. Okay. We have includes. And so typically, in the includes, there's all sorts of different things, and it says, okay, it's STM, Cube IDE, you'd find it in plugins, COM, whatever, new tools, all the way, ARM, Nani, Abby, include, there's a new lib, there's a whole bunch of stuff. So all of these includes, there's the GNU GCC compiler, which is the compiler that's here. There's the new debugger, which is the debugger. The GNU C compiler started out way back when Linus Torvalds wanted to start getting things going to build Linux, a little hobby. Incidentally, 30 years, just a few weeks ago, I think, 30 years that Linux has been around. And it was Linus Torvalds in Helsinki saying, hey, I'm kind of working on a little project and it won't mount too much and it'll only be on a 386, but, you know, I've got some stuff compiling, and here you go. The GCC compiler from the Free Software Foundation he used to go and compile that stuff and put it out there in, this is pre-internet stuff. It was just different government buildings and colleges and universities that were hooked up using mainly bulletin boards and that kind of thing. And so a few other people jumped on board and it took off. GCC originally was the compiler to do 386 stuff. And since then, I think it does 70 different processors and things. It's available in lots of different. It's free. You can go download it. If you've downloaded a Linux of any kind, it's chances are it's already there. It's already installed. Anyway, this uses GCC. And so there's a whole bunch of include files. And so whenever I do anything, it brings in the C standard libraries, all of that kind of stuff. It's a C compiler. There's also a C++ compiler part of it as well. And so if I add any libraries, add anything, I'm going to need to point to the header files that define what all my prototypes are for all the libraries or the different C source files and things that I want to put in. So I might need to add some of the stuff to my project, and I'd be going and looking in there for that kind of stuff. I also have core, and core here has an include, a source, and a startup directory. And so if I go and look at my include, there's a main.h. Now I mentioned main.h, and when you do the graphical environment, main.h is where it puts what you call stuff related to what's there. Okay, so if I go and open up the main.h in here on my hello world, then I could go down and see it says include stm32f4xx underscore hal.h. So it's including another libraries, and I can actually open that. And so you could do something like that, and then go right click, and then go open declaration, and it will go find that and open that header file, and I can go and look down through that header file. And so it has a bunch of different things in there defined. So it's a hardware abstraction layer header file, meaning when I do some of the HAL stuff that it will bring that in. Okay, so just in main, if I scroll down, what do I have? The graphical environment in the IDE let me define green LED as GPIO pin 12. It says green LED port is GPIO-D. Orange LED port is GPIO-D. Red LED port is GPIO-D. Blue LED is GPIO-D. So if I use blue LED port, red LED port, orange LED port, green LED port, then it's all GPIO-D. So that won't make a difference. So if I forgot to change those, it's still pointing to port D. But if I use pin, it's 15, 14, 13, 12. So it knew which ones we were on, because it just, that's where it puts stuff when I go and name things in the graphical environment, okay, main.h. Where that could be a thing is if you have another file somewhere and you're referencing something from your graphical environment, at the top, you need to include main.h because it won't know what you're talking about. It knows what GPIO-D is, but it doesn't know what, green LED is or something like that. Okay, so that's over on this one. Okay, hardware abstraction layer, it.h is, again, another header file for the appropriate .c file, and we'll have a look at that coming up. And of course, our main.c file, that's where it's going to start off, and you see right at the top, it says include main.h. When I scroll down, one of the things that was mentioned last day was, hey, where do I put my code? And there's these begin and end things, and I just you kind of look over them over a while. But to begin with, when you look at it, it's kind of overwhelming with all of this, the stuff that's there. Again, the graphical environment is editing your source files it's ordering, editing main.h, main.c, some other files here, it.h, it.c, all of these different ones. And it's letting you edit too. So there's the graphical environment is editing it and you're editing it. And so the way ST has said, hey, let's make it easy for you to be able to do things and we don't want to accidentally wipe out your stuff. So we'll put tags in the source file, and our graphical environment code generator won't remove stuff between the begin and ends. Okay, so here, if I have some includes, there's an include main.h. Well, I want to use the math library, so I want to include math.h. So the first thing I do is I go and I put include math.h right underneath main.h, and that's awesome, and it compiles and it all works. And then I go and add the blue button, and then so in the graphical environment, I add the blue button and I go generate, and then all of a sudden stuff isn't working because it wiped out the include math.h because it wasn't where it should be because I put it where I've always put it. Okay, that's the one that gets me. I go and put my code in the right place, but I go include something and I just tuck it in after that, and then things work great until I add something, and then all of a sudden I'm getting all sorts of errors and going, what's going on? And it's because I stuck include math.h here and not between the user begin includes and user end includes, which says don't wipe it out when you go change the graphical environment. Okay. One of the nice things that they've done in one of the last iterations of this is user begin header, user end header. I've been more forgiving in past iterations of the course with your comments because I usually want your name, what lab it is, the date, and a sentence or two about what your program should do, because then if you look a year from now and you look at some code, what did it do? Okay, when did you write it? If any of you have been in the TAC course or ever did the little Simon Says, we have a little Simon Says um, uh, project for high schools, and sometimes people come in on checking out electronics and all that, and we do that. I wrote that code in, I don't know, 2008 or something like that. I Some of the function names look familiar. What they do exactly, I'm not sure, and I've commented most of them there. And if it's usually posted online there, you can go see how to build a Simon Says using a PIC microcontroller. But exactly what I did or what to do to up the octave or the tempo or do all of that kind of stuff, or what I'm supposed to pass in to ignore the buttons or whatever. None of that I remember at all. Okay, so it's like somebody else wrote the code, but the comments are there and things that are important are there. So hopefully I can very quickly figure out what was going on. It also has the date, any revisions. So at the top, I will say, I did something, and then I might have, in fact, the compiler changed, and I did something else probably a year or two later to make things still work. And that documentation is in there. So I have my name and what I did, and then above that, then there is the changes and what happened and all that. Some uh, different software projects get so big they have attached, and in the project they have a README with a revision and all the different changes that happen from one thing to the next because it just clutters it up. But you want some sort of documentation. If all of a sudden you go and look at um, uh, things weren't working that used to be working, a production piece of code that you have out there, and you see, there's the clock is off, and you see something going wrong. You go back and you look and you say, oh, Jeremy updated the code for talking to the crystal, 6 months ago. Then you go, okay, we've been having problems for about 6 months. Maybe we should go look at what's going on there, or maybe that introduced another bug. Going down the road, that's also a great reason to use Git, because you can step back to the way it was and see if the problems go away, and then increment back through all your changes over months and find out where the problem is. So again, I'll talk more about that down the road. So we have main.c, user begin, user end. They didn't used to have a tag there. And so every time you guys wrote some stuff up there and documented appropriately and then added a blue button, it would wipe out all your documentation. So we have been just a couple of little bits of documentation. It won't wipe it out now. So you could change that, but leave the user begin and the user end, and say this as the GPIO lab, put your name, put your date, put a sentence, especially the first ones where the documentation might be a little bit more helpful. For instance, you're going to wire up a TFT. It'd be real nice in the TFT if you said what was required to wire it up. Like, because this documentation and everything else is going to be separate. Probably you're going to find this might be pushed to your Git repo, and you want to run the code, and then you go, I wonder what kind of LCD it was, or I want to know, how I'm supposed to wire it up. Just copying, pasting a little thing from your documentation on pinout, and it's all documented there. Okay, so that kind of thing. Again, for the first few labs, a sentence or two is kind of all that's required. Again, between the beginning and the end, so we don't lose stuff. And then we go through, and it has things like the private includes, private type defs, private define. So, if you're defining LCD, I just want to define that it exists. You could, for instance, put it there. Private macros, private variables. So it's giving you places to try and keep it in appropriate places. We have, it says, private function prototypes, and then there's user begin private function prototypes. So that's a good place for you to put your own functions, the prototypes of your own functions, right? So define that I'm using, for instance, in this lab, you could have a function called rotate, which you either go left or right, depending on what value is passed into rotate, or you could have two functions, one called clockwise, one called counterclockwise, and then a do thing. So you would define the prototype for the clockwise and the counterclockwise there, and then a good place to stick it, I'm going to jump all the way down here, a good place to stick that would be all the way down. There is a user begin for and user code begin for and user code end for. So that's a great place to stick all your functions that's out of the way of all of that other stuff, and then the prototypes are defined up top. Okay. Want to go back up. So we've gone through all of those private function prototypes, then private user code. So anything you need to do before main will go there, and then there's main, and again begin and end. So I might have, maybe I have a variable that I want to use at the start of main, and then it does things like HAL init. So the hardware abstraction layer API, to go initialize anything there, that's what it's calling. And then system clock config. Well, if we look at the system clock config function, when you went over in the graphical environment and went to the clocks and set all that stuff up, it made that function. Okay, so remember we did, there's a phase lock loop, there's 336, all of that kind of stuff in that. So when it calls that function, which is down below here, it will do that. And then GPIO init, it again is going to be down below. There we go. And then anything you want to do after all of the stuff is initialized, you could put in here before your while one. And then I've got my user code begin while, end while, and then wrapping by the last brace, whether you want it just before it or just after it of my while one, for instance, you can put something there as well. And then my code goes there. And hopefully when you regenerate stuff, it won't wipe it out. Okay. And so it did a whole bunch of other things there. And one of the things it did just above was it did this. You go there. It did this HAL init. So if I highlight that, it's saying this function is used to initialize the HAL library. It must be the first instruction to be executed in the main program before called to any other. So up above, I can define variables and things like that, but it's not wanting you to do. If I tried to do any calls that used one of the HAL functions, it's not ready yet until I call HAL init. Okay, so It's saying, hey, don't do that. And again, any one of these, if I highlight that and I'll go open, right click and go open declaration, it'll take me to that actual function. System clock config, it's doing a bunch of stuff there, and it's defined just below. And then GPIO init is also there's system clock config. Okay, and it has a whole bunch of stuff. It says RCC. Now you went into RCC to enable and have a crystal, and it says RCC oscillator is external HSE. High speed is on. The PLL is on. There's a 336, an 8, a 4. If you go look in the graphical environment, you'll see those in the drop-down boxes that you set up, and that's where it got all of that information from. Okay. Before that graphical environment, you had to come up with all of these and make sure you didn't miss one of them and that kind of thing. So it set all of that up. Then we have GPIO init. And it says MX GPIO init. And it says GPIO init type def, GPIO init struct equals 0. So there's some sort of thing here. If I go and look at this, then it says, hey, it's got this structure that has the pin and the mode and pull and speed. And it says pin specifies the pin to be configured. Mode specifies the operating mode for the selected pins. And then we have pull. It specifies pull up, pull down. And then we have speed, specifies the speed for the selected pins. And so we have all of that kind of stuff. Alternate, whether or not it's going to be just a GPIO pin or alternate, and it's this type def. So we're having something called GPIO init struct, which is an instance of the GPIO init type def defined for a structure. Okay, and the way that the Cube MX IDE goes and does things is instead of you going yourself and selecting all the different ones and zeros that are in the registers, and you can do that, it will say, hey, we've got a structure, fill in the structure, call the initialization function, and we'll go set the appropriate bits in the appropriate places.
Yeah. Why are the variables inside that structure 32-bit when you said the pins are 16-bit?
Great question. We're dealing on a 16-bit port. A lot of registers, not all of them, but a lot of registers need, because there's so many different configuration options, need more than 1 bit per pin that it's dealing with. It gives us speed options, 4 different speed options, so there's actually 2 bits for each pin to talk about the speed. Some just need the 16 bits, and usually the upper part of that register is left undefined. Okay, or not used, or reserved maybe for future use. And we'll look at some of those, but it's a great point. One of the things to mention, of course, the ARM Cortex system is a 32-bit CPU, and you have been used to 8-bit CPUs with all the PIC. It's native word length. It wants to deal with everything in 32-bit. One of the other things that does for us is we have 32-bit data. We also have 32-bit addressing, which gives us a 4 gig address space. So we have it's not all used, we only have 1 meg of flash, but we have a massive amount of address space that we could put things in. And I'll show you how all of that stuff goes down the road. So one of the things in GPIO init, we have __ HAL clock enables. Somehow that's turning on the clocks for the buses. And it turned on the H and the D clock. I'd have to go look and see why it's turning on the H clock. I'm not really sure, because I do know why it's turning on the D clock, because we're using port D. I don't know what's on port H, but it turned it on as well. So, and that's where sometimes you will find that you go look at the code and it's turned on maybe things for more ports than you want, or more things than you want. And if it was battery backed up, you go through and you turn off stuff that you don't want to use. Okay. It says configure GPIO pin output level HAL write pin port D, and we had called that green port, green GPIO port, red, orange, blue, that kind of thing. And so it's called, it said HAL GPIO, right? There's the port, and then it says green lead pin or orange or red or blue, and then it says put it with reset. So it has ORed those values all together. It has gone and bitwise ORed all of those together. So I'm not quite sure why that is here. We'll have to have a look. And then it says configure pins. Nice, it puts all these comments in. Configure pins, green, orange, red, blue. And so there's this structure, and it has the pin mode. And when we highlighted the structure, there was a pin, a mode, a pull, a speed, all of this kind of stuff. And it does stuff with them. In pin, it says, hey, OR all of these together. Then the output's push pull, which is your standard output. And it says no pull-ups. You can have pull-ups, pull-downs, individual pins if you need something to be turned on to hook up to something and needs to start off low, for instance, or it needs to always be high unless you. So you can, instead of having to put pull-up resistors, you could just turn them on here because it's on each pin you can do that. Speed, it's LEDs. I can't see it as fast as we can toggle it and things like that. So I just need to update things on the LEDs at a low speed. So however you set this up, and again, IntelliSense will work for a lot of this kind of stuff. If I start going GPIO underscore mode, control space, it'll go open drain, push pull, all of this. It'll give me all of those selections. Then the very last thing it does here is the HAL GPIO init. It needs the port that you're working on, and you give it the address of the structure I just filled in. And then that GPIO init function goes and it takes all the information and sets the appropriate bits. Okay? And so that's kind of how all of that worked. Now, it did it for us, but that's kind of how it works. And I'm going to go into a little bit more detail over on that in just a second here. No, no, where is it? Oh. Hey, Edge wants to be my PDF reader now. It wants to be my everything. Yeah, that's really nice. Okay, this is under the week 2 stuff. And it says from halgpio.h. And so when I looked over at my code, and if I go GPIO init type def, it's going and showing me stuff here, but let me just do that. And I'm going to right click and I'm going to go open declaration. There's halgpio.h. And that's, if we go to look at our drivers and I go to the HAL drivers and I go to include, they're all there. Okay, that's all the stuff that's automatically just brought into your project. When it was thinking about generating stuff, it brought all of that stuff in. Okay, so here is the type def that we just looked at. And when I went and highlighted over it, it found the file and it kind of gave me a little glimpse into it. And so there's, I want to have pin and mode and speed and all of that kind of stuff. So from halgpio.h, we have this structure that is defined, and it's called GPIO init type def, and we have an instance of it called GPIO init struct. Okay, it made that all for us. And so in order to fill in the appropriate things, we need to go through and fill in this structure and call that GPIO init, or it does it for us, and it sets up all the bits. Okay, and so one of the things that said GPIO init struct.gpio pin is pin 12 or 13 or 14 or 15. We saw that just now that it did that, and I'm going to, why does it do that? Well, if I go and again look in that hal.h file, in that it shows that GPIO pin 0 is equal to 0x00001, pin 0 selected. And then pin 1 is 2, 4, 8, 10, 20, 40, 80, and so on. In other words, you're dealing with pin 1, 2, 3, 4, all the way up to 16. Okay. It also has one called GPIO pin all, which just sets them all. You want to do everything to the whole port. Okay. When I had my red lead and my green lead and all that in main.h, it associated each one of those with, well, it associated it with pins 12, 13, 14, 15. Well, if you go through and look at 12, 13, 14, and 15, if I'm there, then I have 1,000, 2,000, 4,000, 8,000. Well, that's the upper nibble of those 16 bits. And so when I OR them together, then I'm going to have an F in that upper nibble, 1 or 2 or 4 or 8, all bitwise ORed together, you have 1, 1, 1, 1. Okay, so how GPIO init does is it says, okay, what pins am I working on? And so it looks at this pin mask for ones and does things to those bits. That function will say, you're asking me to do a bunch of stuff. What pins do I do it to? And it goes through and looks for wherever there's a 1, and it does things to those bits. What exactly does it do in things we need to still look at. In the RM0090 1800-page reference manual under GPIO ports, it talks about a bunch of things with it, and it shows you what registers are going to be affected. And so there's a place for GPIO port mode, and it says GPIOX mode register address offset 0. Somewhere in memory, there is a place where I do stuff with GPIOA. Then there's a place where I do it to GPIOB, and then GPIOC. And so there's a base address for dealing with GPIOA. There is a base address for dealing with GPIOB. And all I have to do is pass to the GPIO init function the base address of the port that I want to deal with, and it will say, okay, if you tell me that's where A is, I know everything else is based on that address. So at that address, plus 0, the GPIO init function knows that it has the mode register. Okay, and then so it will look at that. So if I pass in that function, let me go back to main. So how GPIO init, the base address is D. Here's the address of where the structure is. So go work on those pins, whatever those pins were right here, wherever those were a 1, and go do the stuff to the individual registers. Okay? And so I just say, do it to D, and it knows, because it's going to go mode and pull and speed and stuff, because it knows that mode is at offset 0, for instance. It says mode is where, so if I pass it in port D, right at that base address, there's the mode register. And the mode register says, okay, when I hit reset, it's going to have a certain value for the different ports, 00 for all other ports. A and B must have some other things on them that slightly modify that. But here's where it's a 32-bit, and we have multiple things going on. And so, for instance, these bits are written to configure the I/O. So when I call GPIO init, it's going to look at the pins, and then it's going to do things with the mode register depending on what I said. And what did we say as far as the mode? Let me go back there. And it says mode is output PP. Okay, so my options are, for most ports, 00, that's the reset state. High impedance, stay off the line, don't be act like you're electrically connected to anything. That's a default when you hit reset. Okay, general purpose output mode, alternate function mode, or analog mode. Okay, so our general purpose output mode, and so it will look at the different pins, and we were the top 4 bits of the port. And so it's going to look at this one for 15, 14, 13, and 12, and it's going to put a 0, 1 in each of those locations. Now, before they had the GPIO init function, you had to go to wherever this address is, the base address of port D, and then at that location, give a 32-bit word and fill in 0, 1, 0, 1, zeros, all the rest. So I'd go 0, 1, 0, 1, 0, 1, 0, 1, and all zeros for the rest of it. And that's how you would set it up to start to set that stuff up. Well, what's the next thing is mode output push pull. So we have all of the different ones. And then we have a type. And they've kind of put 2 of these together. Push pull is 0, open drain. And we talked about open drain being you have FETs on the output of the pins. And there's no pull up to 5 volts or 3.3 volts mostly is what we're dealing with. There's no pull up. And so if I put something in open drain, you'll get a good low. You can tie multiple outputs together and use a low to signal, and you have one common resistor for all the different outputs. That's one thing of doing it. The other thing that you can do, as long as your current requirements are met, are have a different voltage on that pin and do something with that. Okay, and most of the time, what you're going to want is just be output push pull. That's where the resistor is attached to our VDD line from the output FET, and you get good highs and lows. So that's generally the way you want to put it. Okay. And the thing about this one is that offset from port D was 4, because it's 4 bytes along from mode. Okay, so that's 32 bits, 4 bytes. Okay, so that's your next address. Then from there, the next thing we do is our speeds. And they've kind of changed this. Well, they used to give you the option when you go control space. They used to say 225, 50, 100. Now they just say low speed, medium speed, fast speed, or high speed if your capacitance is right. Okay, and so again, we said low speed, and so you need 0 zeros. And by default, it is 0 zeros on most of the ports, but it will go through and it'll go 0 0 0 0 0 0 0 0. Okay, and this offset is 8. Again, we had the base address, and then you had the next register, and then you had the next register, and then from there, there's pull-ups or pull-downs. When we put it all together, there's also, it turned on the clocks, that was at the very start. It sets it into, to begin with, all the pins being low for outputs. If it is outputs, then it says, hey, work on all of these different LEDs, your push-pull, no pull-ups or pull-downs, the frequency is low, and then HAL GPIOnet says the base address of this is port D, and then this is the structure, and it goes and sets all of those registers up, all of the different bits. You didn't have to, okay? We'll continue on with that. We're going in depth in the GPIO, and then we're not going to do it for the same registers, types of registers. All of that is done for everything else, but the graphical environment sets all that up. It's just you see a bunch of magic stuff there in main. This is where it's coming from, okay? Thanks. We'll talk to you next time.